Good afternoon, everyone. Is the sound good? Okay. And thank you for being here. My name is Akif Akta, and I'm honored to present the work of mine and my colleagues from University of Luxembourg. Our study focuses on enhancing learning by utilizing virtual reality for teaching abstract physics concepts. So, many secondary school students report that physics is one of the hardest subjects to learn. So one reason is that physics deals with invisible phenomena. In general, things you cannot see or touch, but even during lab experiments, you measure those phenomena, but you don't feel, you don't see. The good thing with virtual reality is that it can bridge that gap by making these abstract stuff, the invisible stuff, visible and tangible by creating its virtual environment, which we can modify and work with. So our idea was we took a classic physics lab, in this case shown on the left, a DC motor lab, and then we replicated the same activity in VR. So the goal was to see whether VR-based version of the lab support learning and engagement as effectively as traditional method, or maybe even better. So in both conditions, students follow the same procedure, follow the same goals, but the medium was different. Then we asked, how does learning in virtual reality differ in terms of learning outcomes and learning experiences compared to real lab? So let me start explaining the physical experiment set we have. It is about DC motor setup that many students use to explore the fundamentals of electromagnetism. In this condition, participants physically connected wires and completed circuits and modified certain parameters and observed by taking some measurements with the help of ammeters and other measurement tools. It was kind of physically interacting activity. They followed a printed handbook as a step-by-step guidance. And this setup served as a baseline condition in our study, which we will compare this one with its virtual environment version. And continuing with the virtual environment version, it was developed in Unity and deployed on MetaQuest 3 with hand tracking mode enabled. So we didn't want to use the controllers because we wanted it to be comparable to the real lab version where you use just your hands. Luckily, MetaQuest supports hand tracking mode, which we utilized for this reason. But this time, we can see the electrons, see the magnetic fields, how they interact during the activity. So it basically replicated the real lab, replicated the components, and let's say interaction modes. And we made sure we also have something similar to printed guideline we used in the real version. For this reason, on the back side of on the back wall, we have the handbook guidance step by step, so ensuring that these two conditions are comparable. Continuing with the study design, it's between subject design, where we have two groups. The first one is the traditional group. We have a participant on the left engaged in the activity. As you also see the handbook guidance. And we also have a tablet which is connected to the ammeter just to get some measures, observe and experiment with the kit. And on the right side, we have a virtual reality group wearing headset and interacting with the environment using hand motion, hand gestures. So continuing with participants, we had around 40 participants and 20 for each group, and then they were randomly assigned to either traditional or the VR group. And the study was conducted in the University of Luxembourg's VR AR lab in Belval campus. So let me talk a little bit about the procedure, how it went. And each participant began with a pre-test to measure the baseline of their understanding of the DC motor and electromagnetism. And after that, after the preset, we had the learning activity, which took around 15 to 25 minutes, but participants were informed that they could leave early if they wanted to. And right after the activity, we have immediate post-test to measure comprehension gain. And then follow with questionnaires. We had 2 questionnaires right after the post-test, right after the immediate post-test, situational motivation scale to assess the motivation, and cognitive load questionnaire to measure the cognitive load. And then this concludes what's been done in the lab. And then after 1 week, participants receive an online test, and then similar fashion, they answer with their phones or laptops, and then this concludes the whole procedure. So delayed post-test help us to see how much knowledge those participants kept over 1 week. So it's not only capturing immediate comprehension, but also long-term learning effects. Continuing with the measurements, we have 5 parameters that we compared between 2 groups. First one is the immediate comprehension. We get this measure by comparing pre-test and post-test, and the next is knowledge retention. We compare post-test 1, which is immediate post-test, and the post-test 2, which is the delayed post-test. And the motivational state and the cognitive load are measured from the questionnaires. And we also saved the time spent on task, which is an indicator as an engagement in our scenario, because participants were able to leave early if they wanted to. So these are consisting the learning outcomes and experiences that we compared between 2 groups. Continuing with results. Okay, so starting with the pre-test, both groups share similar baseline knowledge, which is seen on the left column. And we also see significant learning gains when we compare pre-test and post-test scores. But again, the learning gains are similar. After 1 week, the traditional group showed a decline as expected. But here we have something interesting. However, the VR group improved their score slightly during that period. I will also show you the score changes plot for you to see. So comprehension gains are similar, but the knowledge retention is quite diverse. So let's talk a little bit about why it works like this, how VR can lead to stronger retention or even improving scores over time. So the explanation we had is that VR learners tend to have stronger emotions connected to the activity due to environment being more vivid and the activity or VR in general being novel. So this may lead to having better memory encoding. And then we have this thing called mental replay, which participants can replay the activity in their minds, which can act as a mental practice, which can result in better memory consolidation. Of course, this might also happen for traditional participants, but we comment on this one, that VR had more emotions attached to the activity in general compared to a traditional one, because their scores improved after 1 week, which was something interesting. So continuing with the other results, cognitive load and the engagement. So cognitive loads were similar across 2 groups, which is actually a good thing because in VR, you normally, we have added visuals. We might expect to have an increase in cognitive load. But when we consider the time on task, which we have a significant difference between the 2 groups, we are having around 45% longer engagement than the traditional one. So the cognitive loads were comparable, but the time on task was greater on VR, which says that even they spend more time, the cognitive load were manageable. Okay, so the motivation levels were high across groups. And the interesting thing here, we have this gap a little bit wider for the identified regulation, which shows that the VR group had more personal value attached to the activity than the traditional one. which might have resulted in that difference, but it should be noted that it's not significant difference. To better understand how different parameters interacted in our study, we conducted correlation analysis across all main variables that I shared earlier, but two of them showed meaningful relationships. The one related to time on task and motivation. We saw that people spent more time, had more motivation, or vice versa. The more motivated ones stayed more on the task. And the same applies for the cognitive load, which is something expected. The more time they spend, the more cognitive load they have, according to based on the subjective questionnaire. Okay, to sum up, we had similar immediate comprehension between the VR group and the traditional group, but VR learners retained more knowledge or even improved after 1 week, and engagement was higher in VR without having a cognitive load, which is a huge plus on that side. And motivation scores were comparable, slightly higher in VR, but again, statistically not significant difference. So we can easily say that VR helps to transform that abstract knowledge into a more memorable experience that lasts longer. Thank you for listening. That was all for my presentation. We can continue with Q&A.
Thanks for the presentation. Out of curiosity, did you do a correlational analysis for the time on task compared to the learning, particularly the retention?
Yes, they were also included. We didn't find any, let's say, significant correlation.
No significant correlation?
No.
Okay, all right. Thank you.
You're welcome, no worries.
Yep, next person, please. Thank you.
Hi, thank you for the presentation. I was wondering, is there any particular reason you choose virtual reality over mixed reality or augmented reality? I'd imagine that projecting information on actual real-life object would make the experience more grounded and memorable for students.
To be honest, we wanted to have a more controlled environment, so that's why we stick to virtual reality. But of course, this study can be extended by adding augmented reality side to the table. So it is, of course, doable for a future study.
Thank you.
You're welcome.
Yeah, just one more question. Thank you.
Okay, I've heard of cases where utilizing multiple sensory devices, including tactile displays, improved learning outcomes. Did you consider this as well when you researching this project?
Okay, I couldn't.
Sorry, your sound was a little bit muffled because of probably your mask. Yeah,
sorry.
thank you.
I've heard of cases where utilizing multiple sensory devices, including tactile displays, improved learning outcomes. Did you consider this as well?
So tactile input. Have you considered having tactile?
So for future, let's say, work, we consider those. It is, of course, doable. I think adding haptic to the table would make research more, let's say, diverse. And I think future research should focus on that as well. But for this one, we kept visual as a main focus, but future studies, yes, haptic should be investigated in this aspect.
As a future, okay. All right, thank you.
Can I ask one more thing?
We are slightly running behind the time. If you can kind of get connected during the breaks,
yeah, sure.
That would be great. Thank you.
No worries.
All right, so.
Good afternoon, everyone. I'm Yi Xinshen from Beijing Institute of Technology. Today, I'm excited to present our work, titled LightEdge, a data lightweight and user-adaptive VR telepresence system for remote education. This work is with Wei Liang from Beijing Institute of Technology and Jianzhu Ma from Tsinghua University. So today, education is gradually shifting from face-to-face learning to remote learning. This transformation breaks the physical boundaries between teachers and students. It is particularly valuable during the COVID-19 pandemic and in resource-limited regions. The most commonly used tool is 2D video conference platforms such as Zoom. While enabling real-time communication, this platform falls short of capturing the richness and the engagement of face-to-face learning. So a key question is to answer how to enhance the sense of co-presence in remote learning. I believe that telepresence shows a promising solution. It allows users to feel present in a location beyond their physical surroundings. Previous work focused on 3D screen like a virtual cube or holographic projection such as room-to-room. However, these approaches lack a strong sense of embodiment and co-presence, limiting user engagement and learning retention. Virtual reality has revolutionized the field of telepresence. It offers unprecedented immersion that brings students closer to real-time experience. It also can empower students shift from passive recipient to active participants in the learning process. The method has primarily focused on point cloud-based method, such as live science 3D. However, the resulting models often suffer from poor visual quality. The second is nerve-based method. For instance, shared nerve employ continuous volumetric representation to produce photorealistic results. However, this method requires long training times whenever the sense changes. Moreover, both pipelines involve complex encoding and decoding process, increasing the risk of data loss. So to design a virtual reality telepresence system, we faced two major challenges. First, achieving low latency is non-trivial, and maintaining high fidelity rendering under this constraint pose a greater challenge. The second challenge is within the virtual classroom. We need to answer how to allow users to obtain an optimal viewing experience. So how to address these two key challenges? Inspired by recent advances in Gaussian splitting, we employ it for efficient optimization and real-time rendering, make it ideal for latency-sensitive telepresence. For the second challenge, we use a graph-based viewpoint recommendation model to enhance the user experience and simplify interaction. Therefore, we propose light-80 system. On the teacher side, only a single camera is required. And the motion data is estimated, and the system sends the motion data inside of dense point cloud or large image sequence. And the motion data can drive a dynamic human model rendered with the reconstructed classroom in students' VR headset. Moreover, light-80 generates optimal viewpoint tailored to individual preference. From an implementation perspective, light-80 consists of 2 stages, the pre-class preparation stage and the in-class teaching stage. In the first stage, the teacher records both the classroom environment and the teacher. This data is transmitted to remote students. And the students can reconstruct the static classroom and the teacher's canonical 3D model. Specifically, we first apply structure from motion to generate a sparse point cloud of classroom. Then we employ a standard Gaussian lighting to reconstruct its geometry and appearance. The Gaussian parameters are optimized by a loss function that ensures the color and the structure consistency. In human modeling, we first estimate the simple X parameters and anchor them in animatable 3D Gaussian into the simple X mesh. Each Gaussian is associated with learnable attributes that enable post-conditional appearance variation. To optimize Gaussian parameters, we use a multi-term loss function that ensures color and structure consistency, enhance perceptual similarity, and constrain the learnable Gaussian parameters. In the second stage, the teachers record the lecture and estimate the simple parameters for each frame. The motion and audio data are transmitted to remote students. Each motion field only requiring 2 kilobytes. And then the received motion data drives the human model rendered with the static classroom in the student's VR headset. And we also employ a user adaptive viewpoint recommendation to optimize the optical viewpoints. So specifically, each 3D Gaussian in the canonical model is deformed into post space via linear blend scanning driven by the estimate simple X parameters. During sense combination, we first adopt a shared camera coordinate system to ensure spatial alignment. Since the simple X estimation operates under a weak perspective assumption, so minor scale discrepancy may occur. So we also apply minor scale adjustments to the human model to improve geometry alignment. In the viewpoint recommendation model, candidate viewpoints are represented as the graph node. It is evaluated based on 4 evaluation factors. The first is training set similarity. It measures a viewpoint approximate to the distribution of training set. Human approximately ensures that each viewpoint have appropriate distance from the teacher. Environment occlusion measures how much the teacher is obstructed by surrounding objects. Historical user attention reflects the long-term attention a viewpoint has received. In the graph, edges represent spatial continuity to ensure smooth translation between viewpoints. If the edge is too large, the edge. If the angle is too large, the edge is removed. The graph is updated by a dynamic optimization mechanism. We first update the weight of the score functions using Reggie regression model. Then we refine viewpoint position using finite difference method. During viewpoint recommendation, the edge weights will be converted to effect edge cost. The cost is computed by direction cost function and the scoring function, which penalize abrupt viewpoint change and favor nodes with high quality scores. The path from current to each candidate node are evaluated, and the optimal viewpoint is selected. Quantitative experiments demonstrate our system achieve lower latency, particularly during transformation, as only 2 kilobytes of motion data needs to be synced. User study also confirm our reconstruction pipeline. The viewpoint recommendation module deliver better performance across multiple evaluation metrics. LightEd has a strong potential for applications such as laboratory training, procedural teaching, and collaborate learning. In summary, we present LightEd, a VR telepresence system that combines lightweight data transformation with high fidelity rendering. We propose a user-adaptive viewpoint recommendation model that considers visual quality and user preference in dynamic scenes. We also validate LightEd through quantitative experiments and user studies, showing improvement across multiple metrics. Thanks for your attention. For more detail, please refer to our project website or our paper. Feel free to contact me via email or WeChat. Thanks.
Thank you. Let's thank the author. Thank you. Any questions from the audience? If you can raise your hand, we'll bring the microphone to you. While you're thinking, I have a question regarding the 3D modeling of the teacher. I think you used the canonical model and animated it afterwards. How detailed of facial expressions or hand motions can the canonical model express?
You mean how to drive the human model dynamically?
So how much details can the facial expressions and the finger movements can
the simple X model have all body skeleton and the hand skeleton, but we haven't to model the face expression because it needs more and more devices to capture the skeleton.
I see. So might be something that you might want to look into in the future to add more details to the human.
What?
Maybe it might be your future work that you are looking into, add more details to the motions in fingers and facial expressions, probably.
Yes.
Yeah, sure. Thank you. Any other questions from the audience? Otherwise, let's thank the author again, and we'll move on to the third paper.
Exactly. So today I'm presenting on behalf of the first author, who is Tobias Rau. He cannot be here. He is currently writing up his thesis, so I'm gladly representing him today. So this talk is about chemistry, and I think I had chemistry definitely once in school, and I liked it a lot, but some of you maybe didn't like it that much. So of course we have teaching materials to support students and teachers alike to improve this kind of teaching situations. For example, you may remember these model kits where you can kind of assemble your own molecules. And these are great because they're tangible, you can collaborate with other students, so it's really a good teaching material. But of course, it's harder to build up larger structures, it takes some time, and it's also not easy to overlay additional information. It's actually not really possible, right, because it's a physical model. And then we have, of course, also 3D representations that we can show, for example, on a desktop, like here. And these are great. You can load huge molecules, and you can also overlay information. But the problem is it's hard to collaborate with these kind of 2D desktop molecules. So this brings me to our research question. So we've asked ourselves, how can we bring in AR into this? So how can we actually improve the situation for teachers and students? And so we thought of how can we support students and teachers in AR by communicating visual attention. So this is a core aspect of our work. And so for this, we came up with a hybrid approach, which comprises an immersive part, where kind of students wear an HND and they can interact with molecular structures immersively. And we have a teacher here in the background using a desktop application to monitor the students, how they're doing. In immersive environment, I have a video here. Here you can see me and the other cohort, Nelusa, and we're currently working on this molecular structure here in an immersive environment. And you can see we can do certain interactions with the molecular structure. And this is based on ChartPack, which is a framework that the first author, Tobias, actually developed. So with ChartPack, you can actually load up molecules in AR, and you can manipulate them. For example, here you can see how someone is tearing apart a molecule. You can also combine molecules to larger structures. And we have different interactions. You can point, gaze, and edit. And what we added on top of this framework is kind of a attention feedback mechanisms. For example, these circular highlights, which I show here. So you can see how this looks like. So we have, for example, 2 or 3 students looking at this certain atom, and then we have individual segments on this atom that light up as they look at this. And then you can see here, for example, if all 3 of the students are looking at it, we have this full circle, which displays shared attention, kind of. Okay, this is the immersive part. Now let's switch to the teacher. So as I said, we have a desktop application that the teacher is using to monitor the students. Here you can see 3 students represented by these boxes in the scene. The scene itself we scanned with a LiDAR scanner, so it's a point cloud that is also incorporated in this application. And we have the students, and of course we also have the 3D molecular representation in the scene. And what's very important about this desktop application is that we also have a 2D mapping that is kind of mapping the 3D representation in a 2D space. And this is a structure formula. It's a very common representation in chemistry. And this has a lot of advantages for the teacher. So there's no occlusion. And this really improves certain things like interaction. Of course, there is a mental load involved that you have to consider, but still, you can do, for example, clicking on atoms to highlight them also in the immersive space to guide attention. And that's something that is much simpler here on a 2D representation. And then we have also feedback based on the gaze. And so we have gaze heat maps that are updated live for each student, P1, P2, P3. These are 3 different kind of panels. And each of them show the current attention on the molecular structure. I have here a video that maybe demonstrates this a bit clearer. So here on the top right, we see it's basically the same molecule, just copies. And on the top right, we see the selection of the teacher to guide attention. And here, the 2 other windows are showing the gaze heat maps that are updated continuously, of course. And you can see here that this kind of also aligns, the heat map align with the selection that the teacher made, which shows, okay, the student actually look at this. Okay, this is about the desktop application. So far I have, I think, outlined these 2 spaces. And now it looks like maybe that to you, that students and teachers live in separate spaces. But that's not actually the case. Because what we also implemented is that the teacher can also wear an HMD and stand up, like this is the desktop application. And now he is kind of standing up and going to the students and maybe demonstrating in an immersive environment something, which sometimes can be very helpful. Okay. Let's talk a bit about the evaluation. So what we did, we demonstrated this approach to 2 doctoral students of our chemistry department, serving as teachers, and we had 6 undergrad chemistry students. And we performed 2 tasks, kind of. The first one was much more complex. The second one is a bit simpler because it involves a smaller molecule, which you can see here. And I'm only talking about the second task now. So there are several subtasks involved. The first one was find existing potential stereocenters. So that may sound very cryptic to you and to me as well. So what that boils down to is kind of finding the specific carbon atoms that are highlighted here. And of course, the students only see the 3D representation. You have to take that into account. So they had to kind of find these specific carbon atoms. In the second task, they had to kind of classify, is this glucose molecule an alpha or beta variant? And in the third task, they actually had to manipulate the 3D structure. So they had to tear apart something, or they had to combine smaller molecular structures, or to just manipulate it, basically. Okay. While the students performed these tasks, and also the teachers were kind of monitoring the situation, we looked at the teachers specifically, and we had our observations, of course. So for the first task, we noticed that the teachers were using the heat maps a lot. That makes sense, because they were, of course, monitoring if the students are actually looking at the right carbon atoms. In the second task, the teachers were actually guiding attention a lot with the highlights. So clicking on the structure formula and highlighting these atoms in the immersive environment. And in the third task, we noticed that teachers actually transition sometimes to the immersive space to demonstrate the manipulation. So this is similar to the video that I've shown you, where this teacher was standing up and then kind of going to the students. Okay. Of course, we also collected participants' feedback. So we first asked the teachers what they liked and what they didn't like. So the teachers really liked attention guidance, so clicking on the atoms, highlighting them. They really liked attention guidance, monitoring with the heat maps as well. And something that we noticed, then they kind of reported to us was a bit difficult, was this 2D, 3D mapping. And for this glucose molecule that I just shown, this is rather small, right? So this is simple, but for larger molecules, this mapping is kind of difficult to do. And that's something they reported to us, and they said, okay, they would need some preparation time before the teaching lesson to just learn that. The students also liked the momentarily highlights I was showing before. They really liked the immersive environment. They liked it more than these stick and model kits. But sometimes they found it difficult to edit the molecules, to manipulate the molecules in parallel, because these are sometimes destructive operations, right? You're tearing apart a molecule. And that's something that is not so great if everyone is sharing the same. So one idea would be to just have duplicate copies of the same molecule and everyone is doing their own operations. Okay, to conclude, we have some lessons that we learned. So for example, group sizes, that's very relevant, right? So we noticed that group sizes should not exceed 3 to 4 students because of course the teacher has to monitor. And if we have so many heat maps at the same time, that's of course something that gets very difficult. Another thing, the context switches of the teacher should be minimized. Even though they're really helpful, doing that like back and forth, desktop, immersive, it's really disruptive. I only talked about chemistry today, but of course, there are also other domains where we could apply this approach, for example, in architecture or in electrical engineering. So basically everywhere where we have some kind of canonical 2D representation, 2D mapping of the 3D structure. Okay, in terms of future work, currently, Tobias, the first offer, is supervising a student who's kind of building a tutorial system for Chartpack and specifically for this approach, just to improve the onboarding experience for teachers and students, because this is something we noticed. Of course, you have to provide them some instructions before they can actually use the system. Last but not least, of course, post-analysis is something that was not considered here. This is live monitoring, but that's something that could be also very interesting to look at, like replaying teaching sessions and so on. Okay, thank you very much. That was it, and I'm happy to take your questions now.
Yes, thanks, Order. Thank you very much. Any questions from the audience, please? Yes, gentleman up here.
Thank you so much. Thank you for the interesting presentation. So I was curious if you know about the technical architecture of this work, like how did you implement this?
Yeah, this was actually Tobias' part.
Okay.
So, but I can tell you a little bit. So this was Chartpak was of course the foundation.
Mm-hmm.
So this is where we actually can load up molecules in the 3D space. We also of course used networking protocols. I think Reptide, I'm not sure if that says something to you. That was a networking protocol that we used to have
The
some
collaboration,
communication between the HMDs and the desktop.
Uh-huh. How about the collaboration between the users having the HMDs? Was it as smooth as you see in the video, or there was glitches? Because usually it's not that smooth.
Yeah, we had actually a QR code marker so as a reference. So they had to register that marker before, and then the kind of alignment was quite fine.
Mm-hmm. Yep, thank you.
Yes, you're welcome.
Thank you. Any other questions? Maybe we have time for one more questions. If not, I'd like to ask a question regarding, so your next future work, you mentioned about tutorial system. Can you kind of explain a little bit more about how you're going to use the attention guidance in that kind of scenario or in the context of tutorial system, please? Thank you.
Again, I would need to ask Tobias about the details. He just told me. So I'm not sure how much the attention guidance actually is relevant in this. I think so. I think it would make sense to also include that in the instructions. But I think, no further details.
Okay, thank you. Thank you very much. Thanks the order. The presenter again. Thank you very much.
Thank you.